Coming to page 4 of our notes, doing just a little quick overview of what we talked about. I love this visual. Not It's really heavy in notation. Do not overthink it, right? The idea here is that we are working with these 3D surfaces. We take a plane, right? Here's that plane that we talked about on the previous video. We intersect that plane. And then what we get is a 2D curve, right? That you see right here. And I'm actually going to trace over it just so we can really see it. Right here, there's the trace. Looks like this is where y is constant, and we can do the same thing for x, right? We come over here. We do get a similar shape. Remember, we've learned that the traces don't have to be similar shapes, right? This is where y is constant. This is where x is constant, right? And then if we were to essentially pick a point, let's say we'll use this one, call this point AB. What happens is that the partial derivative, let's actually highlight some of this stuff. The partial derivative at that point tells us instantaneous rate of change of the outputs, we call them F, with respect to, let's say, x, when y is fixed at B. For this one, where we have x equal to a, right? We're going to look at the partial derivative with respect to y at some other point. It doesn't matter what we call it. We're looking at the instantaneous rate of change of the outputs, right, with respect to y when x is fixed, right? So those are some of our notations. We've got a little bit more notation down here. And that's, let me go ahead, kind of box for you some of the main notation that we're going to run into, right? We'll work on this. This tends to be the most common. Notice it looks kind of close to what our old notation, the ddx. This is not a 2. This is like a weird squiggly D is the way that I like to think about it, right? So this is not a 2. It's kind of like I was saying, like a weird D, for instance. But what this means in words, right? So not a 2. I don't know how to write that. More along the lines of a weird D. Right? And what this means in words is this is the partial derivative. Still derivative. Sometimes I forget to say partial. Of f with respect to, for this one, looks like this one we have an x. The other one we have the partial derivative with respect to y. And then this AB, right? This line means evaluated at. So let's write that. Evaluated at the point AB. So kind of just unpacking the notation a little bit. So the common notation that we're going to be using is these ones down here. I would say that the most common one would be probably this one and this one, right? So the partial derivative of f with respect to y, the partial derivative of f with respect to x. So this one is the partial derivative with respect to f. Partial derivative, of f with respect, oh my goodness, to y. Look at me dropping parts of my sentences. Right, so let's work on that. Right, so let's kind of say it together. The partial derivative of f with respect to x, the partial derivative of f with respect to y. What we're trying to figure out here is what's happening to these outputs as each one of these inputs is changing. So there's going to be this theme, which means when we're computing partial derivatives, we are going to treat one variable as a constant while we analyze the other. The thing is we're not going to want to plug in values all the time, right? It's very time consuming. And so thinking about these things, so this is a big one. This is what we want to do. Essentially, y is going to be staring at us in the face while we're trying to think of it as a constant, right? So let's take a look at this page. Rules for finding partial derivatives of our z surfaces described by the function f of x, y, right? So let's come back to this 4 minus x squared minus 2y squared. If I wanted to find the partial derivative with respect to x evaluated at a point, right? Your first step is to find the first order partial derivative. So find partial derivative. And it's telling you what letter to use. And this is how we're going to do it, right? So I'm going to treat y like a constant. I'm not going to plug anything in for y, right? I want you to get into the habit of being able to find these partial derivatives at other points, at any points, having generic, right, descriptions of these things. So I want to find f of x, which is the same as the partial derivative of f with respect to x, right? And so I'm going to take the partial derivative with respect to x of my function. My function was 4 minus x squared minus 2y squared, right? And the idea here is you've got to be able to stare y in the face and be able to go, you're nothing but a number, right? So treat like a constant. And it gets funky. It's hard to wrap your mind around it at first. You got to get really used to it. If you're comfortable with derivatives, this generally comes to people pretty quickly. This function should look familiar when we're done because it's the same function we were working with earlier, right? So think of it just a regular derivative like you've been working. What's the derivative of 4 with respect to x? 0. What's the derivative of negative x squared with respect to x, right? This is where power rule comes in. Minus 2x. What's the derivative of 2y squared with respect to x? Well, remember, y is a constant, and the derivative of any constant is 0. So minus 0. So we get our minus 2x. So that should look familiar from the previous page when we got that negative 2x. So for part number 2, because we are trying to figure it out at a particular point, right? Here's our point 1, 1. What we're looking at right here in this picture is it's common that this point is being projected onto the domain. We want to make sure that the values that we're choosing are in fact in the domain, right? So what we're looking at, here's the 3D image, our surface described by this function. Here is that plane. Here's the trace, right? We picked the point, and now what we're going to do is we're going to plug that point in, and we're going to find the slope of this line. So in part 2, how to find the slope of that line, we are going to plug in that point 1, 1. We don't need to plug anything for z, right? Because that's our output. We're going to figure out what is happening to z. So how we're going to write it in notation is the partial derivative evaluated at the point 1, 1. That's how we say that in words. That just means plug in 1, 1. There's only an x value. Yes, it is possible to be left with a y. We'll see some examples of that. And I get negative 2, which was that slope that we got originally, right? So there's my slope, negative 2 of that line. Right? So just layer per layer is what we're working with here. Let's do one with respect to y, because I feel like x is a little bit more obvious. We're used to it. We've done it. Let's do the y one, right? And I'm not going to write out the steps again. You know what they are. I want to find the partial derivative with respect to y first. Or we can write it as the partial derivative of f with respect to y. So the partial derivative with respect to y, our f function was what? 4 minus x squared minus 2y squared. And now we're going to treat this portion like a constant, right? So this is going to be constant. Now I'm taking a derivative with respect to y. This is not implicit differentiation. This is straightforward, take a derivative like you're used to, just with a different letter, right? So let's go piece by piece. The derivative of 4, right? Any constant is 0. So the derivative of x squared, since it has no y's, is also 0. The derivative of 2y squared, power rule, 2 times 2 is 4y, right? Drop that power, and I get negative 4y. So if I wanted to evaluate the partial derivative at a point, 1, 1, right? So this is partial with respect to y of f evaluated at 1, 1 is. That's how you say that entire statement in words, right? The partial derivative of f with respect to y evaluated at 1, 1 is, let's plug it in, negative 4 times 1 is negative 4. So what we did, here's our 3D surface. We did an intersection with a plane, created this curve, right? The plane was where x is constant now, right? So it's like somewhere along this x value. We traced where that plane intersects the curve, so there's the trace. Then we see how things are changing at a specific point, and that change means our outputs are going to reduce by a unit of negative 4 for every y value increase of 1. All right. Go ahead and flip it to the next page. Let's do some more. Let's just practice with some partial derivatives. Remember, this weird notation, not a 2, right? We're using our same shortcut rules that we used in Calc 1. So you've got to be able to recognize them. We've got our solutions here so that way we can double check our work. Remember, product rule, quotient rule, chain rule, all that stuff. Even this stuff where we had to rewrite our roots still apply, and the negative exponent stuff still applies also, right? So all of that is still true. Let's be really lengthy in our process. So here is our function. Let's see if we can match these answers. Our goal is to find the partial derivative of f with respect to x and y. So let's do x first. Remember, this means treat y like a constant. So I'm going to take the partial derivative. I'm going to write a lot of steps. There's definitely a lot of this that you can skip. I'm going to be very thorough. So my function is x to the 4th y plus x over y squared. I'm just going to do some old rules from way back when. I'm going to zoom in just a little bit. Just helps me. This is kind of what's happening in my brain a little bit. Remember, with your derivatives, you take, if they are separated by a plus sign, you can just take the derivative of each term, term by term. Then you can take the derivative of the variable that you're interested in. Since we're talking about x's, I'm just going to kind of isolate all my x's, right? So I'm kind of making that little pink is kind of like my mental note. Everything else is going to come out to the front because it's constant, right? So I'm going to take the partial derivative of x to the 4th and multiply it by that constant y at the end. This one, I've got a 1 over y squared, partial derivative with respect to x of x. Remember, y squared is in the denominator. You cannot take it out. Put it over under 1. So then, now what we're focused on is taking the partial derivatives with respect to this. Remember, we just multiply those constants in at the end. So, what's the derivative of x to the 4th? 4x to the 3rd, just like you remember from Calc 1. 1 over y squared, partial derivative with respect to x is just 1. And then I'm just going to kind of clean my notation up a little bit. 4x to the 3rd y plus 1 over y squared. There's my partial derivative with respect to x. Now we can kind of start to see why knowing which variable, whether it's x or y, is important and needed in the notation. Okay, so let's do it for y now. This is the partial derivative of f with respect to y. Remember, those aren't 2's, they're weird d's. And my function was x to the 4th y plus xy squared. I'm going to be very thorough in my steps. Feel free to skip what you'd like at this point. All right, I'm going to take the partial with respect to y of each term. Again, this is a lot of what happens in my head, not so much that I write it, these 2 steps that I'm writing out right now. So this one where I can kind of distribute the partial and then pull out the constants. Again, this is the stuff that I do in my head. But don't forget, whenever you see stuff like this, you got to rewrite using your negative exponents. Okay. So x to the 4th derivative of with respect to y is just 1. Plus x derivative of essentially y to the negative 2nd, right? Bring the negative 2 down, subtract the power of 1, so negative 3. Last step, clean it up. X to the 4th. I'm going to switch this to a minus because we got the positive times the negative. I'm also going to rewrite it without the negative exponent. So I've got my negative 2 times x over y to the 3rd.